Well, it's a real pleasure to be back amongst my friends at University of Toronto. I think of Toronto as scintillometry central, and that means a lot to me because I have a great interest in the kind of projects that are going on here. And when Viswesh contacted me about giving a talk, he suggested that it might be useful to get an update on what our NANOGrav collaboration is doing and where we are in the process of trying to detect gravitational waves in another gravitational wave window. So that's what I'm going to do today. And this isn't my bread and butter sort of talk. And so I'm leaning heavily on contributions from several of my colleagues within NANOGrav, Maura McLaughlin, Steve Taylor, and Sarah Burke-Spillar, who have contributed slides and content to this talk. So in some places I've given proper attribution. In other cases I've just put their slides in. But I'm very appreciative for that. So NANOGrav is a large organization. There are something like 100 people in it now. And I want to, for this audience, I want to note that there are 3 Canadian institutions at least represented here. Jing is the Toronto representative, and then Vicky Caspi and her group at McGill, and Ingrid Stairs and her group at UBC are very important members of our NANOGrav collaboration. And so we are one of 3 major collaborations in the world that are trying to detect gravitational waves using pulsars. And the other 2 are one based in Europe and one based in Australia. And as you can see from this plot, though, that of course leaves out several emerging radio astronomy forces, namely India, China, and South Africa, all have major contributions to make in upcoming years, and I'm sure they're going to be folded into the efforts to detect gravitational waves. And before I go any further, let me just say it's fine with me if you interrupt me during the talk. So if you have any questions or want clarification as we go along, please feel free to just stop me.
Where in Europe is it? What country is that?
Excuse me?
Where in Europe? What country is that?
Where in Europe?
Yeah.
So the 5 telescopes that they use in Europe are the Jodrell Bank telescope, the Effelsberg telescope, Westerbork in the Netherlands, the Lovell telescope in Great Britain, and then there's a telescope in Nancy in France, and then in Sardinia there's now a new telescope. So those are it sounded to me like I said 6 telescopes, but there are 5 major telescopes that are in Europe. Was that? Yeah, that was your question. Okay. So this is the idea in broadest brush, namely we time pulsars, and we now time about 75 pulsars. We keep very accurate recording of every spin rotation of the neutron stars over baselines now approaching 15 years, and in some cases even a little more. And what we're looking for is we're looking for coordinated irregularities in the arrival time of the pulses from these pulsars. And as you know, gravitational waves are a quadrupolar wave disturbance that propagates and a transverse wave, and as those transverse waves come out from a source, and I'll be talking about the sources of these gravitational waves in a few minutes, they disturb the metric around the pulsar, around the pulsars, and around the Earth. And that disturbance of the metric at the instant of time that the radio waves are emitted from a particular pulsar, and at the instant of time that the radio waves are detected at the Earth, causes an effective Doppler shift, and that effective Doppler shift changes the arrival time of the pulse, and it's looking for slight retardation of pulses or slight advance of the pulses. That is the main signal that we're looking for. And we're looking for this as a coordinated pattern around the sky. And this is parameterized by something known as the Hellings and Downs curve, which goes back to 1983, a very early analysis not long after the discovery of millisecond pulsars. And in this analysis, the idea is if we have a stochastic background of gravitational waves, and we're looking around the sky at a large ensemble of pulsars, what we need to focus on is we need to focus on the relative angles between two pulsars in the sky. And then even though the metric disturbances at those two pulsars will be uncorrelated with each other because they're in general going to be at quite different distances from us, the portion of the metric disturbance from the gravitational wave at the Earth causes a correlated either retardation or advance of the timing signal from the pulsar. And this is it's a positive correlation if the sources are essentially in the same direction in the sky. And if they're approximately 90 degrees apart, there is an anti-correlation. And then 180 degrees apart, it's partially correlated again. And this again follows from the quadrupolar nature of gravitational waves, and it's absolutely essential to what we're trying to do because there are many sources of noise in the experiment, and it's only by being able to see a coordinated pattern around the sky and this coordinated correlation that we can unambiguously detect gravitational waves. So let's talk about the sources of the gravitational waves that we're trying to detect. So most of you in the room know the basics that I'm going to go through in the next few slides, but I just want to remind us all. So we have an evolving universe, and so as the universe comes out of the dark ages and galaxies start to form, galaxies start to coalesce. And we know that the galaxy formation process and the subsequent evolution of galaxies is a hierarchical clustering kind of scenario, such that small building blocks are building up into larger and larger galaxies as we move later in time in cosmic history. And this is absolutely essential to what we're trying to do, because what we're trying to, our primary source, we think, for gravitational waves in the wave band that we're sensitive to with pulsars is orbiting supermassive black holes. So we're, a dream source for us is a 10 to the 9th solar mass black hole, a 10 to the 9th solar mass black hole, orbiting each other with a period of, let's say, a year or so. And wouldn't it be nice if that were just 10 megaparsecs away? So we don't think that that particular dream source exists. I'll show you some limits that we have on supermassive black hole binaries in the Virgo cluster in a little bit. But that is the sort of scenario that we're looking at. That's the kind of source that we're interested in. We're not looking at the merger event itself. That's outside of the gravitational wave band that we're sensitive to, but we are looking at this long period of time over which the supermassive black holes might have a separation of a fraction of a parsec, and they're in a regime where they are primarily losing energy or giving off gravitational waves, and that is the primary energy loss mechanism at this point. And so the evolution and the shrinkage of the binary orbit is taking place because of the production of gravitational waves. And so this is all very familiar stuff to us because we live in this remarkable era in which gravitational waves have been detected. Now, of course, they've been detected by the ground-based interferometers, LIGO and Virgo. But, you know, this is very exciting stuff. And, you know, just a couple of weeks ago, we got a new version of this black hole neutron star merger from all that we can tell. So this is just showing that we start off with two galaxies 50, 100 kiloparsecs apart, and then as tidal friction takes over and these galaxies merge, we end up with a merged galaxy, and the supermassive black hole that was at the center of each one of those galaxies then drop to the bottom of the gravitational potential well and find each other and go into orbit around each other. And there are obviously lots of details that are left out in this picture, but as I was saying, the region of orbital separation from about 1/10 of a parsec to about 1/10,000th of a parsec is kind of the sweet range for us with pulsar timing arrays. And then I wanted to note a couple of other things before I leave this slide. So then, as this slide shows, the laser interferometer space array, LISA, would then pick up this signal as the coalescence approaches, and then there's an actual merger event, and then most of you won't be able to see this, but maybe the people in the front row can see that in a black hole merger event, it's quite possible, depending on the spin orientations of the black hole, to end up with actually a permanent offset in the metric of space-time, or and that offset propagates outward at the speed of light, and that this is a so-called burst with memory. And the pulsar timing arrays again are sensitive to actually to the memory effect associated with that kind of a merger. And so this is just showing the different gravitational wave detection bands. This is the LIGO band. This is you know, an in-spiral of stellar mass black holes, tens of masses of solar mass black holes. LISA is weeks to months kind of coalescence, and pulsar timing array is many months to years for the orbiting. So we actually don't know a tremendous amount observationally about supermassive black hole binaries. There are my colleagues who study this in detail, in particular Sarah Burke-Spillar, who made this slide, is pointing out that there are actually no no completely clear detections of supermassive black hole binaries so far. They're very hard to detect when they get that close to each other, but nevertheless, it seems inevitable that as galaxies merge and as the supermassive black holes in those individual galaxies get close together and go into orbit around each other, that there is going to be that kind of those kind of sources at the center of many massive galaxies in the relatively nearby universe.
Are there any candidates where you expect that to be galaxies with irregular shapes, where they clearly either measure that in the recent past?
Yeah, there are definitely multiple candidates, and people use spectroscopy to to look for periodic variations in the light output down at the nucleus of a merged galaxy, and there are tantalizing sort of hints, but there's nothing that just absolutely has been confirmed. Yeah. And yeah, so that was the main thing that I wanted to say there. And then there's all kinds of, I mean, one of the things that I like so much about this field and being a part of a collaboration is that you learn a lot along the way, and in fact, as we get more and more stringent limits and move toward a detection of gravitational waves with pulsar timing array, there's a lot of active galactic nuclei physics at the center of the in this case of AGNs that come into play and then give rise to other sorts of signals from these sources, not just gravitational wave signals. And in fact, I should emphasize that one of the things that we're most hopeful about is that this is going to be a multi-messenger kind of effort, such that our pulsar timing array collaboration and others ultimately detect individual sources, and that then those individual sources can be traced back to sources that we can see in electromagnetic waves. So I like this comparison. This is, I got these slides from Steve Taylor, but I saw just at the end that he got them from Sarah Burke-Spillar. In any case, what is being shown here, if you can see it, this is about to expand quite a bit, but this is Galileo in 1610 in the visible portion of the spectrum at 10 to the minus 6 meters, looking at Saturn. And so in 1610, that was the electromagnetic landscape. But some years later, we have a much richer view of the universe and many more techniques, much wider electromagnetic wave spectrum. And you all know this, and we've grown up, many young faces in the crowd, you're growing up in this period of time when this is just a given, that you have friends working on gamma ray observatories and people doing infrared work and lots of people doing radio work. And of course, the whole electromagnetic spectrum is wide open. And then, of course, we also have neutrino astrophysics, and we have cosmic ray astrophysics. And so, already there's a multi-messenger world that we live in. And what we're attempting to do with colleagues around the world is open up the gravitational wave spectrum in the same sort of way. And so we're talking about three sort of wave bands in the gravitational wave spectrum, defined more by detection techniques than anything else, although there are of course, there are different sources in the different regimes as well, the different portions of the gravitational wave spectrum. And in this particular case, what's being focused on here is the frequency of the gravitational waves. So as you know, gravitational waves travel at the speed of light. And so there's, of course, then a wavelength associated with these gravitational waves. And so if we have a 1-year period to the gravitational wave, we're talking about a 1 light year kind of wavelength to the wave. And the pulsar timing arrays are down around 10 to the minus 9 hertz. So this is something like the inverse of a year, and this is the region of sensitivity, and this is now the characteristic strain, little h, that we're sensitive to, and these are then the sources that might be giving rise to a signal in this portion of the waveband. And so the supermassive binaries supermassive black hole binaries are our primary source, although other things that get mentioned at least are primordial, there could be primordial gravitational waves that from an inflationary era that then make it into the current day, and another thing that gets talked about anyway is cosmic strings and interacting cosmic strings that could then be giving rise to gravitational wave background as well. So that is pulsar timing arrays. Here, maybe I should have started over here. This is the one that we know works, right? This is LIGO and Virgo. And here's gravitation GW 150914, the first detection of a gravitational black hole merger. I think we probably all know where we were when we heard the news that this had been detected, and is a very exciting moment. And of course, one of the marvelous things about the LIGO and Virgo, the ground-based interferometer gravitational wave detection, is that because these detectors are detecting the gravitational wave itself, the metric disturbance itself, as opposed to the power in the gravitational wave, the fall off of the strain falls off as 1 over r from the source rather than 1 over r squared. And that, of course, is absolutely crucial in terms of the future of gravitational wave astronomy, because with the 1 over r fall off, it means that if you can improve your sensitivity of your detector by a factor of 2, then actually the number of events that you can expect at that sensitivity level is going to go up by a factor of 2 times 2 times 2. It's going to go up as the cube of that sensitivity improvement. And so a factor of 2 improvement in detector sensitivity, which is, these are quite attainable kinds of improvements in the realm that we're working in now, can give you almost an order of magnitude increase in the event rate. And we're going to be seeing the consequences of this in the upcoming years, because LIGO, we're all going to be hearing about gravitational wave coalescences all of the time, because as more detectors are deployed and their sensitivity improves, it's just going to be like boom, boom, boom. I'll just mention in passing that this is also true for the pulsar timing array regime. We're also detecting the metric disturbance itself rather than the power in the gravitational waves. And so, again, as we start to detect individual sources with pulsars, then as we improve our sensitivity by a factor of 2, we're also going to increase our event rate by something like an order of magnitude.
The kind of, according to 1/r, I agree with all of that. I think so you mentioned the gravitational waves from the Big Bang and also core-collapse supernovae. In these cases, I think the neutron modes are not the dipole mode, the higher moments. I think they decline faster. So you don't.
Okay, so the comment is, for those of you who might not have heard, the comment is that for core collapse supernovae, that the gravitational wave signal is not primarily a dipolar signal, but higher, or quadrupolar, but higher order moments. And I can't. I'll just have to take that I'll just take that as being true, in which case then the fall off would not be 1/r. But that's I'd have to. We should explore that further. But that's a useful comment. So this this again is just the range that we're talking about here, just to give people. So the frequency, from 1 per several week to 1 per several years puts us in this range, 10 to the minus 6 to 10 to the minus 9 hertz. The gravitational wave strain that we're sensitive to is roughly the arrival time accuracy that we can attain over, let's say, a 10-year kind of timing baseline, divided by that 10 years, and so that's a fractional. That's a fractional strain of, or that's a strain of 10 to the minus 15, which is a dimensionless quantity. And I just want to re-emphasize this because it is just pretty extraordinary that the timing that we're doing and our colleagues are doing around the world, this is phase sensitive, where the phase that I'm talking about is the rotational phase of the star. So every rotation of the neutron star is accounted for, and then what we're talking about when we're talking about 200 nanoseconds, we're talking about something like 1/1000th of a rotation of the neutron star over a 10-year kind of period. And so what we do is we predict, based on current observations, we predict where the pulse ought to be arriving, let's say 10 years from now, and then we observe where the pulse does arrive, and the difference between that, the residual, is what we then inspect for the presence of the gravitational wave, for the kind of the disturbance due to gravitational waves. So a few other details that I want to pass on to you about the actual, about our detector, namely about the pulsars that we use. For those of you who are pulsar aficionados in the crowd, and I know there are many of you, you're of course very familiar with the period derivative diagram. This is pulsar period, log of pulsar period horizontally, log of the period derivative vertically, and this is the main distribution of pulsars. But starting in 1982, thanks to Sri Kulkarni and Don Backer, we found out that there is another family of neutron stars with a different evolutionary history, and these are the millisecond pulsars that were born in binary systems, and as the binary companion evolves, it donates mass onto the first neutron star, and that spins up the neutron star to periods, orbital periods that are of order a few milliseconds. And so these neutron stars, these millisecond pulsars, are ideal detectors for the pulsar timing array. One, they are very old sources, typically 1 billion years old or older. So sort of their young and restless energy. I'm looking at all of you younger people in the crowd have kind of quieted down. And so they are very smooth rotators. They're also rotating very quickly, and they tend to have very sharp pulses. And so, so they can be timed very precisely. And so they're for many reasons, just excellent, excellent components of our detector. Now, I just want to show a few slides to emphasize the fact that pulsar timing isn't quite as simple as it sounds. It's not just a clock and a big radio telescope. There are all kinds of things that need to be worried about. As the specialists in the crowd, I'm thinking of Jing and others. Many of you have timed pulsars and have put together packages that Jing, perhaps you know, is the person who has created a completely new pulsar timing package called PINT. And this is now the standard timing package that NANOGrav is using. And there were many things that you needed to think about along the way, and many, many effects that affect the arrival time of the pulsar. Some of them are summarized here. And this is just a set of slides that that shows this in I think a pretty clear way, although it's only clear if you can read the text. And none of you, except perhaps Daniel, will be able to read the text. But these are different parameters that get estimated from the pulsar timing. These are 3 different models that we have that are primarily, they differ from each other in the way that the noise in the signal has been modeled in 3 different ways, and so we end up with slightly different values for these parameters in the 3 different columns. But I just want to highlight several things here. First of all, the most basic thing is that pulsars have a spin period, and they lose energy, and as they lose energy, they slow down. Okay, and so they're spinning down, and so we have a frequency and a frequency derivative, and then so those are the spin parameters, and here, and then pulsars are located somewhere in the sky. They have an RA and they have a deck. They also have a proper motion. Okay, and so all of that needs to be accounted for very carefully. And all of these things, if you don't have the way that these values are improved upon as you gain more data, is that there are certain characteristic patterns in the timing residuals that that emerge if you don't, if you don't have the period or the period derivative correct, or if you don't have the position, or you don't have the proper motion. All of these have their own signature in the timing residuals, and then many of the millisecond pulsars that we time are actually in binary orbits around typically a white dwarf. But some of them are in orbit around other neutron stars, but most of them are in orbits around white dwarfs. And so there is a large number, a large number of parameters that both Keplerian and post-Keplerian that need to be estimated in order to account for the binary motion. When all that's been done, as I mentioned, we talk about the residuals, which is just the difference between the expected arrival time of the pulse and the measured arrival time of the pulse. And this is a fairly typical kind of plot. This is -3 microseconds up to 3 microseconds. This is from 1993 to 2013. And so we've got 20 years of timing data shown here for this pulsar. And these, and one of the things that's being shown here is the improvement over time in the instrumentation that we're using, such that the most recent data collected for this pulsar, which extends right up to the current day, is being timed to a much higher precision day to day, or observation to observation, because these are not daily observations like once every week or once every several weeks, but these black points are the sort of the state of the art for our instrumentation. Yeah.
It does seem that it's just Arecibo, which is way better, because I see ASP, which is also Arecibo in green, which is almost as good.
Yes. Yes. And so, right, and no, that's a good point, Martin. Yes, no, absolutely, yeah. The telescope really matters. And this slide summarizes some of the sources of noise that we have to worry about. And I'm not going to go through every square here, but let's just to call things out. So for one thing, we know that even millisecond pulsars, at least in some cases, do not appear to rotate perfectly smoothly, but have rotational irregularities that are a source of noise. But that source of noise, this column is saying that is not frequency dependent, where the frequency dependence that's being talked about now is radio frequency. So is it achromatic or not? And then there's something called pulse jitter, which is basically saying that what we do is we measure an average profile of a pulse, and that average might be like a 2-minute average of all of the pulses that have come in for this pulsar that's spinning around 600 times a second or 300 times a second. And that forms up into almost the exact same template that it did the previous 2 minutes ago, but there is actually slight variation in that, because it's a finite number of pulses and the individual pulses jitter around or jump around, and so there is there's an averaging effect there that's basically based on the finite number of pulses included. And then something that I'm going to talk about in a little bit more detail in just a few minutes is that the interstellar medium is quite problematic, because these pulsars are moving through space, and as they move through space, the sight line through the interstellar medium changes, and that sight line, the total electron content along that line of sight is not the same, and also the multipath scattering along the line of sight changes with time as well, and that scattering delay then is also a time variable thing. And if we're talking about ultimately what we'd like to do in the next 5 years, is we'd like to get down to sort of a 10 nanosecond precision with our pulsar timing, and at the 10 nanosecond level, there's quite a lot to worry about out in the interstellar medium. And then I'll just say quickly that, in fact, one of our current limiting sources of noise is the model of the solar system that we have to depend on, because we have to correct for the motion of the Earth around the solar system barycenter, and that can only be done as well as the planetary ephemerides are known. And I'll show you a slide in just a moment about the fact that yeah. No, not glitches. Fortunately, millisecond pulsars haven't been seen to glitch. This is more like a red noise kind of timing process, which is actually not yet well documented for millisecond pulsars, but there's a suspicion that for several of them, they are showing that same kind of rotational irregularity that many young pulsars show. Okay, so I want to then try to get into some interstellar medium things in just a few minutes, and so I'd like to just show you a couple more highlights of our observing program, but then go on to some of the current results from the NANOGrav program. And so as this slide says, we've got 76 pulsars in our current grouping. This is a list of many of those pulsars, and now what's shown here is from 2004 to 2016. These are individual observations, and that's the kind of data set that gets pulled together. And we do this on a 1.5-year cadence, and in addition to the kind of results that I'm going to report in a second, I just want to emphasize, and this is something that we always emphasize with, when we talk about this work, and also when we ask funding agencies for support. There is a tremendous amount of synergistic science that comes from this program. There's a lot that we learn about neutron stars and about millisecond pulsars. In doing this, we've discovered, the collaboration, people in the collaboration have discovered a very massive neutron star recently. There's lots of tests of general relativity that get done by looking at both neutron star binaries, but also neutron star white dwarf binaries. And then we're learning a lot about the interstellar medium. And particularly this is highlighting that when people detect very massive neutron stars, it then helps to constrain equations of state for neutron stars, which is very fascinating physics. So how about some results? Okay, so the only results, the results that we have released to the world at this point relate to our 11-year data set, which has been which was published several years ago. We're working on the 12.5-year data release. It's almost ready to go, but not quite. I'll show you just one or two results from that. But this is a sort of key plot. It's not the only way that we analyze these data. I should say that all of the results are ultimately done in a completely Bayesian sort of framework, in which basically we have all of the parameters that are being estimated, but then we're looking for the expected correlations, and we're doing this very much in a as I say, in a Bayesian kind of analysis, because we're not expecting gigantic signals. We're expecting a signal to emerge over time. And this is the Hellings and Downs curve that results from the 11-year data set. And the red line here is indicating the preferred model for the correlation here. It's a very it has the proper shape for the Hellings and Downs curve, but it's very low amplitude at this point. But I'll show you something about that in a second. And this is just a slide to indicate how serious the problem is with the ephemerides. That we use ones from JPL, and here are 4 different solar system models that they've produced, and those 4 models produce very different sensitivity curves for the same NANOGrav data, and we've had to develop a technique where we basically do essentially a weighted average of the of several of these different ephemerides in order to basically come up with a better model for the solar system than in fact JPL's employing for their spacecraft navigation, because we need to know the solar system barycenter to about 100-meter accuracy.
So we once had undergraduates who did a project to constrain a possible additional planet using these data. So
and so that was using pulsar data. I don't I think I remember hearing about it, but I don't remember the result. My guess is that that person did not find that extra planet, or we probably would have heard about it. But it's definitely also kind of an offshoot of the high precision timing, is basically constraining the not only the masses but also orbital parameters of particularly the mass of planets. So the limits that we're starting to set, we have not yet detected gravitational waves from a stochastic background, but the limits are starting to get quite interesting with regard to various predictions for the background of stochastic waves. This slide is slightly out of date. I'll show you one in a moment that's more that gives you more of the current situation. But like here we have a pessimistic scenario for merger of supermassive black holes, mergers of galaxies, I should say, and then the stochastic background, so pessimistic, moderate, optimistic, and this shows us digging down, and this is our sensitivity curve here, and it depends on, just like the LIGO sensitivity curve depends on the exact frequency that's being observed at. The same is true for ours because of various sources of noise that we have. This one at 1 over a year is due to the fact that that we're blind to anything exactly with a 1 year period, or almost blind to it, because that is completely covariant with positional offset effects in our data. And so here's a slide that I thought might interest you. So as we go from our 11-year data set to our 12.5-year data set, this signal that was preferred in the 11-year data set continues to be preferred in the 12.5-year data set. Now I do have to, draw attention to the fact there's obviously quite a lot of overlap between these data sets. Many of the same pulsars are in there, but there are new pulsars, and there's certainly new, there's new data. But in any case, this is intriguing to us that this signal seems to be strengthening. And this is the more up-to-date version of where we are, or almost up-to-date. Namely, this is kind of the band now of gravitational wave amplitude that is expected from a stochastic background. And our sensitivity curve actually moves downward in a fairly fortuitous manner over time until we actually reach the background, at which point it's a different sort of process. But this is all pre-detection. It's a 14-year data set. We're actually, and then we're looking at a 15 and 15.5-year data set. So I've been mostly highlighting stochastic background, but I want to mention the fact that we are also looking for two other gravitational wave signals. One is from individual sources, you know, very loud sources that happen to be in our band, and for those it depends quite a bit on our distribution of pulsars around the sky, and so this is a sensitivity to continuous wave signals and then this is how far out we would detect a signal. This is in megaparsecs. This is 20 megaparsecs over here. This is 120 megaparsecs over here. And so you can see in some portions of the sky we're sensitive to very deep reaches out into space, at least for us. But then other portions of the sky, it's a much lower sensitivity limit, and that comes about because of the fact that our pulsar source list is dominated by northern hemisphere pulsars. So I'd like to just finish my talk by talking about, just for a few minutes, talking about the portion of this that I and the people that I collaborate with in NANOGrav and outside of NANOGrav are trying to provide to the collaboration, namely dealing with the interstellar medium. And so in addition to total electron content toward an individual pulsar, which the dispersion measure of that pulsar, which changes with time as the pulsar moves through the interstellar medium. There's also scatter broadening, which is a minor effect at high frequencies, but becomes very big effect at low frequencies. We tend to observe in the from about 800 megahertz up to several gigahertz for most of our NANOGrav observations. Those of you who know me know I can't resist showing this slide of wonderful, rich dynamic spectrum over here, and our friend the scintillation arc over here, and various little patches of power there that move and behave in ways that are well known to people, to some of the people in the audience here. And this is a slide that I like to keep coming back to. We analyzed data from a series of 36 roughly weekly observations of a normal pulsar now. This is not timing data. This is inferred time delay that comes from taking the so-called secondary spectrum. This isn't the only way to do it, but you can take the secondary spectrum. You can collapse this power onto the vertical axis here, the delay axis, and you can use that to get a time delay estimate. And we did that for 36 observing epochs, and we did that for 4 independent observation bands for this particular pulsar, and found that over this period of time there was actually quite a lot of activity, not unexpected, but quite a lot of activity of this extra time delay due to scatter broadening, due to multipath scattering in the interstellar medium, but it's time variable. If it were not time variable, then no big deal. It's just an offset to the arrival time, but the fact that it's time variable means that this is something that shows up in our timing data, let's say for a particular millisecond pulsar, that contributes, red noise to the signal, but it's red noise that we're trying to detect in the gravitational wave background. So it's very, it's a very serious problem. Just going to close with a few slides. This is work by Bill Coles and his collaborators. This is just a simulation. This is several hundred nanoseconds of time in this simulation. This is the, you can think of this what this amounts to is this is the impulse response function of the interstellar medium. And so reading this vertically upward, we're looking at a grayscale that we sort of, the signal arriving from the pulsar comes out of the abyss and then rises up to a plateau and falls off. And so, in other words, this is a scatter-broadened edge to the pulse arrival, and then the white line is just the mean arrival time. And this then is some measure, let's call it observing days. It's scaled in dimensionless units, but this could, we could arrange it so this was observing days. And then you see that we've got both small scale structure and larger scale structure here, and lots of there are some beautiful and intricate kind of events that happen. Wei Li and I and others were talking about this at lunch, and this even, I love this because this shows the kind of complexity that you can get. Now this is a logarithmic plot, and so it's highlighting features that are not quite as dramatic as this on a linear scale, but in any case it shows the rich structure that exists out there caused by multipath scattering changing over time. This is a zoomed in version of just a portion of the Cole simulation. And finally, I wanted to end by highlighting the wonderful work that's being done in the scintillometry group here, led by Wei Li Pen and Martin van Kerkwijk, because it really is world-leading work in developing the techniques necessary to detect very subtle time delays in signals. And one of the applications of this that we want to employ these new techniques in order to be able to correct highest precision pulsar timing and remove the effects of these time variable delays in the pulsar timing array signal, thereby significantly improving our sensitivity to gravitational wave background. So I'll just put up my summary slide here, and thank you for your attention, and be happy to answer any questions that you've got. Thank you. Yes?
So there's a prediction that if you have cosmographic turbulence in the ISM, then after you correct for the dispersion measure, there's going to be a scattering tail that scales as the frequency to the power of -4. So is this something that you see in your observations? Or?
So just to repeat the question, it's about scattering tails and scaling as 1/frequency to the 4th. And broadly speaking, yes, we see it in our data, although primarily we observe pulsars that are not very heavily scattered, and so primarily we don't see the effects of scattering in the time domain, but we focus on the manifestation of scattering in the frequency domain, and thereby try to detect it and correct it. But more to your point about the 1/frequency to the 4th scaling, there have been a number of detailed studies looking at the exponent of that scaling law. Most of them come out with a shallower sort of scaling than that, and there are various proposals for why that might be happening. What I find most compelling is that the scattering is actually not from some kind of, isotropic Kolmogorov sort of scattering disk, but we know from a lot of the work that's been done by the Toronto group and elsewhere that the scattering disks oftentimes appear to be highly elongated, and that. And that softens that radio frequency scaling. Other questions? Yes?
So you mentioned NANOGrav is the most sensitive survey, so how is the sensitivity improved if you can combine with all?
Yes, I'm glad you asked that question. So so there's an organization called the International Pulsar Timing Array, the IPTA, and the International Pulsar Timing Array is actively working to combine the data and has combined the data from the 3 major pulsar timing arrays and has its own data releases. And we've done, within IPTA, we've done a data release 1, and now there's a data release 2 paper that's just about to be published. And the short answer is that things improve a bit when you combine all of the data in our current way of doing things. They don't improve as dramatically as you might hope at first, or at least at the moment, simply because it's very hard to take all the disparate data sources from all of these different telescopes around the world and combine them effectively. But this is a very active area of development, and we're trying to move forward on that. And let me just, as people are thinking about any other questions that you have, there was something that I forgot to mention way back at the beginning, but NANOGrav is very strongly supported by the U.S. National Science Foundation. We are a physics frontier center. There are only 6 such physics frontier centers funded at the moment in the United States, and so we feel very fortunate to be one of them. We are just finishing up our 5 years of support as a physics frontier center, and are applying for a next 5 years of support. So if any of the senior members in the room are sitting on review committees that will be looking at that in the upcoming year, please please look at all the wonderful science that we're doing and treat us well. So other questions or comments?
Yeah, we're starting to get time. We may want to wrap up down here and head upstairs for cookies and snacks.
Cool.
Before that, so I'll thank Dan one more time for a great talk.
Thank you. Thanks very much. Nice to be with you. And just go ahead and double click it to turn it off.
There's another one in the